Hello, welcome again to FlippedHarber for Algebra 2. In this video, we're going to talk about rational functions. Our objectives for this lesson are to look at how to write and graph rational functions, how to graph transformations of a really simple rational function. We're going to identify holes in the graphs of rational functions, as well as identify where vertical asymptotes in rational functions occur. And then we're going to end by learning how to identify where the horizontal asymptotes in rational functions are. Our outlines for this video, we're going to start by talking about our first rational function, the inverse function. Then we're going to look at how to transform the inverse function. And then we'll move on to more generic rational functions as a whole. How to find the holes in those rational functions, how to find the vertical asymptotes of those rational functions, and how to find the horizontal asymptotes of those rational functions. Now here is our first rational function that we're going to look at, the inverse function. It's f of x equals 1 over x. Now this is a pretty cool graph. Okay, we've got some graph going on over in the first coordinate. We've got some stuff going on over in the third coordinate. Nothing going on in the second and the fourth. Got some really cool features to talk about in this graph. It's got a horizontal asymptote. Now, this horizontal asymptote happens to be the horizontal line y equals 0. Now, all horizontal asymptotes are y equals a number. Sometimes that number is 0. Now, what this horizontal asymptote means is that this graph going off to the right and off to the left gets forever closer to that line, but it never reaches it, never touches it, never goes through it. Now, along with this really super cool horizontal asymptote, it's got a vertical asymptote. Now, like all other vertical asymptotes, this should be written as x equals a number. In this case, it's x equals 0. It's basically the y-axis. Again, this means that the curve going here up and here down gets forever closer and closer and closer to this vertical line, but it never reaches it, never touches it, never crosses it. That's what an asymptote does. Now, if we want to talk about transforming this basic rational function, the inverse function, we're going to do it just like we've always done it. If we have a number adding or subtracting the x, that's going to move it left or right. If we add or subtract a number all the way at the end, that's going to move it up or down. Absolutely nothing changes. It's just where these numbers are that you need to get used to for each type of function. So I went ahead and I graphed this transformation to the basic inverse function. 1 over x minus 2 plus 3. Now let's stop and think about what each of these do. This minus 2 right here is going to move the whole graph right 2 units. The plus 3 is going to move, get my circle there we go. That plus 3 takes that whole graph and it moves it up 3. Now this graph looks exactly the same, it's just in a different spot. Well, you know what? That does the exact same thing to these two asymptotes. Our horizontal asymptote got moved up 3. Our vertical asymptote got moved to the right 2. So our new asymptotes are y equals 3, that's for our horizontal asymptote, and x equals 2 for our vertical asymptote. So those asymptotes move around with the transformed function. All right, now let's talk about rational functions more in a generic case. A rational function is a function that is made up of a polynomial on top, so I call that p of q, p of x, divided by a polynomial on the bottom, so that's q of x. Now those are just labels. I don't think you'll see them ever again in this video. It's just a reminder that the top is a polynomial, the bottom is a polynomial. Now, some important feature of these graphs. There was no hole in the previous graphs, but one thing that we're going to have to identify are holes in the graphs of these functions and the vertical asymptotes for these functions. Now, the best way to deal with these things, absolute best way, whether we're talking about holes or asymptotes or anything else, factor out the polynomial that's on top, factor out the polynomial that's on the bottom. Even if you just do this and you don't even cancel, let's say that we just totally ignore this for a second. I can see where important features happen. Things like holes and vertical asymptotes happen where the bottom equals 0. So cool stuff is going to happen where x minus 1 equals 0. Cool stuff is going to happen where x plus 2 equals 0. And I spot those so easily because I've taken the time, just a couple seconds really, to factor these polynomials out. Now, is it a hole? Is it a vertical asymptote? Well, now we got to get into that. But let's go ahead and take a look at our simplified version of this polynomial. So I canceled out my x minus 1's, and that left x plus 1 on the top and x plus 2 on the bottom. Now, holes occur at values where the bottom is 0, but specifically, holes happen where the bottom equals 0 and the term cancels out. So this x minus 1 is what creates the hole. It's where it equals 0 on the bottom, and it's the piece that canceled out. So if I look at a graph for this, and I use Desmos to graph this just because I love Desmos, even though I don't actually see it, I know that there is a hole at x equals 1 because if I tried to plug 1 into the original function, it would blow up. I can't have 0 on the bottom of this fraction. Now you can kind of see where my vertical asymptote is, so let's take a minute to talk about that. My vertical asymptotes happen where the bottom equals 0, but it does not cancel out with the term on the top. So the x plus 2, it's a spot where the bottom can equal 0, but it doesn't get canceled out by any terms on the top. So there's not a hole, there is a vertical asymptote at x equals negative 2. It's the term that didn't cancel out. All right, now, while we're here, let's talk about finding the zeros. All we got to do is set the top equal to 0. Now, the top equals 0 only at negative 1. It does not equal 0 at 1 because that part canceled out. Remember, we canceled out the x minus 1. So this part doesn't get a chance to make another 0. All right. Now, let's talk about finding horizontal asymptotes. Horizontal asymptotes occur under one of two conditions. Okay, so these are basically rules of thumb for you to follow. Do I even need to bother to find horizontal asymptotes? My first condition is when the degree of the bottom is bigger than the degree on the top. Now, what do I mean by degree? That's the highest power on our polynomial. When the degree on the bottom is bigger than the degree on the top, you always have a horizontal asymptote, and that horizontal asymptote is always y equals 0. Okay, no work to do. You don't have to show me any work. You just have to point out that that degree on the bottom is bigger. The horizontal asymptote is y equals 0. Now, when the degree on the top equals another, where's that horizontal? It's at y equals some number. We're going to have to do some work to find out what that number is. Obviously, I'm going to have to show you an example. All right, so here are three different, where do they have horizontal asymptotes and which one does not have a horizontal asymptote? I'll give you a second. You can write them down. You can try to figure it out for yourself. Here we go. Asymptote. When the degree on the top is bigger than the degree on the bottom, no horizontal asymptotes. The middle one, g of x, since the two degrees are the same, it does have a horizontal asymptote. We're going to have to do some work to figure out what it is. On the bottom one though, h of x, since the degree on the bottom is bigger than the degree on the top, you don't have to do any work. You just have to state that that has a horizontal asymptote because the degree on the bottom is bigger, and that horizontal asymptote is y equals 0. Alright, so let's take a look at that one that had a horizontal asymptote. I want to find out where it is. I want to find out what that a value is. Well, the way I'm going to do it is I'm actually going to do this division. Don't forget that when you see a fraction, it's really division. 2x squared plus 3x plus 6 divided by x squared plus 2. Now what I'm going to do is some long division, and we've done this. It may have been a little while. You may want to go back and take a look at your notes or look at the videos. I'm going to start by taking a look at this 2x squared and divide it by this x squared. Well, 2x squared divided by x squared is just 2. Now I'm going to take this 2 and I'm going to multiply it around. 2x squared plus 4. Okay, so I went 2 times x squared to get 2x squared, and I took that 2 times the 2 to get the 4. I subtract this out. I have 3x plus 2. Now, I stop. Why do I stop here? Because now this degree, which happens to be 1, is less than the degree that I'm dividing by. I'm dividing by an x squared. So as soon as my degree that I'm working with becomes less than, not less than or equal to, as soon as it becomes less than the degree that I'm dividing by, I stop. Now, what I have right here, it only took me one step to actually find it, is that a value. So I know that this function has a horizontal asymptote at y equals 2. Didn't even take me that long to figure out. Okay, that's it. Now it's time for you to try some of these on your own. I'll see you in class, and I'll see you online.